Welcome to the course on Introduction to Electrical Engineering. We will have a lecture 18 today on the topic of two port network, the part 1. Starting with introduction, we will go for various single port and two port application in practice, and then we will talk about impedance and admittance matrix of two port, then the terminated nonlinear two ports, followed by exercise and numerical problems, and then of course followed by differences. So, coming to the introduction of this, you can call it two port network. We have a concept of like a one port which define any electrical circuit with input voltage and current symbol, we call it like a single port. Similarly, we have a two port also, that we have a like one input and maybe another output or another input to this linear network, and where the first input is like a V 1 I 1 and V 2 I 2, that is the typically we call it two port. So, many electrical circuit we will find which are used in practice might have a single port or two port or even more than two port, but in general a large number of circuits are related to two port. So, we will like to discuss the concept of two port, how we can probably solve the problem related to the two port network like So, a pair of terminals through which the current may enter or leave a network known as a port, and two terminal devices or elements such as resistor, capacitors and inductors result in one port network, and four terminal or two port circuit involve elements like operational amplifiers, transistor and transformer, and a port is an access to the network and consists of a pair of terminals, and the current entering one terminal levels through the other terminal, so that the net current entering the port equal to 0. So, we have a circuit which can be considered by their terminal variables. So, voltage and currents are the terminal variables, and the complex circuit can be analyzed more easily. That is the why we are considering to take this terminology of like a two port network, and there are many kinds of two port parameters by which the circuit can be analyzed, and we will look into the out of many methods that which method is supposed to be the simplest for a particular circuit of either of single port or two port or multiple port. So, coming to now basically a concept of various single port and two port practical application in the field. So, let us take example of single port devices. So, we have here the single port extractor, typically intelligent flow control. Through closed loop control of flow, it ensures constant suction and typically save the consumables, and this we call it single port fume extractor. Similarly, we have another typically a AQE single port extractor, that is extractor is used for power DC IP and PTZ cameras, access control, door closure and other similar equipment, kind of supply typically. And similarly, remote share access single port 4K display port. Another example is like a AQE single port POE extractor. Then the typically the electrical serial port server, considering the industrial one port RS232 or RS422 or RS485 serial device server, or this IP serial device converter transparent transmission serial data communication device supporting web managed system. Then industrial modulus Wi-Fi serial port device server, then typically microphone, then one port serial device server, then typically single port surge protector device with cable HPXN, then the serial adapter Cardbus PCMCIe adapter for RS232 DB9 COM port, then serial adapter another one adapter for RS2 COM port. Now, these are the example of course single port. Now, we have examples of two port devices in practice. So, typical example is a regenerative ropeway with the concept of two port, power can flow or subsea HVDC transmission. Power flow can be also in both the direction in that way, and like or active front end filter, typically for some manufactured by some automation, active front end filter by ABB, or like a transmission network, especially having a transmission line as a kind of two port network. From one end maybe the you can call it supply, you can call it the sending end, another may be the receiving end, or it can be like a vice versa. So, this is also like a 2-port network, or your HVDC transmission, or like a transformer like a primary and secondary with 2-port network, or like a switches, I mean like a BJT or MOSFET as a symbolic representation of 2-port, like a input and output we define for this either like a transistor amplifier, as you can see here with the parameter. We will discuss later on about these parameters with the typically 2-port network, or typically like a dual AC/DC converter with the passport ultra dual converter, or regenerative active filter like a active harmonic power filter, or regenerative battery charger. So, IGBT based regenerative battery charger which can charge and discharge the battery like or you can call it like a regenerative again another battery charger by Signotron, or active front end converter by MTech, or regenerative grid simulator with the typical power rating for different settable voltage and frequency, regenerative grid simulator. Then another regenerative grid simulator by another model of Chroma, or broadcast test set, or power line pass through Ethernet adapter. Then active front end induction motor type, typically like a delta type, because they have input and output port, and 2-port network. Now, these are the example of 2-port network, and now let us come to typically analysis of 2-port network, how we define the parameters and how we really analyze the 2-port network. So, this example like in generalities with the 2-port network. So, standard configuration of a 2-port is that you have the network where you have input port like with the voltage applied V1 with the current drawing or fed into I1, and on the port 2 the voltage is V2 and the current going from port 2 to the network is I2. So, a 2-port network has 2 terminal pairs acting as access point, and the current entering one terminal of a pair leave the other terminal in the pair, and 3 terminal device such as transistor can be configured as a 2-port network. So, now talking about like a we define different parameter of these network, electrical network. So, one is the Z parameters or impedance parameters. Z is like a typically impedance, we have a notation for impedance as Z parameter. So, we will talk about the impedance parameters of the network. So, we consider here the same network with the 2-port network where we have a input port like V1 voltage applied, and when it draws the current I1, and from our maybe output port we have a voltage applied V2 and we have a current entering to the network to I2, and we can write this equation for volt ampere equation for this in terms of impedance parameters of 2-port network, like a V1 V2 will be equal to in terms of I1 I2 multiplied the impedance matrix which have impedance 4 impedance parameters like Z11, Z12, Z21 and Z22. So, these are the 4 parameters for the 2-port network in terms of the impedance, and these can be of course can be defined as well as can be measured or can be calculated from the network configuration. Like we will discuss of course with the example about the calculation of this, or in simplified equation form or scalar form this matrix we can return the relation V1 equal to Z11 I1 plus Z12 I2 and V2 equal to Z21 I1 plus Z22 I2. And where we can define how we can define these parameters, we can define here the if output is open, typically an input we apply the source. So, current of the input will flow, but of course, if output is open then current will not be flowing from the output. So, we can define Z11 V1 upon I1, that is because it certainly will draw the current because you have connected the voltage source for the input, and similarly the Z21 that is V2 because voltage will be certainly coming at the output port even you do not connect the load like even open circuit divided by I1. So, these are the 2 parameters defined from the input side because they are function of I1. In both cases the I1 is coming as a denominator. Then to find out other 2 remaining parameters we do in case of output we connect again the voltage source, but input we keep it open. So, that is the reason means I1 is 0 and from V2 I2 current flowing into the network. So, we define here again first Z22 that is V2 upon I2 and Z12 that is V1 upon I2. Voltage will certainly get reflected even at the input when you apply the voltage at the output. So, we can determine the Z parameter finding Z11, Z121 and Z12 and Z22. So, these parameters how we can really define Z11 V1 upon I1 when I2 equal to 0 means output port is current is 0, because when complete network is in action then you cannot define the parameter. So, Z11 is the impedance seen looking into port 1 when when port 2 is open, and Z12 V 1 upon I 2 when I 1 is 0. So, we say Z12 is the transfer impedance, it is the ratio of voltage at the port 1 to the current at port 2 when the port 1 is open. Similarly, Z21 V 2 upon I 1 when I 2 0. So, Z21 is the transfer impedance, it is the ratio of the voltage at port 2 to the current at port 1 when port 2 is open, and Z22 V 2 upon I 2 when I 1 equal to 0. So, Z22 is the impedance looking from input port into port 2 when port 1 is open. So, these all 4 2 port parameters, impedance parameters, Z11, Z12, Z21 and Z22 are defined in this manner, as well as even existing network also you can find out by make a measurement also in exciting in this manner like. And now, we can say there is a condition for reciprocity of the this 2 port network, where you have given a, that is a 2 circuit A1 A2, where you are short circuiting the output and the I 2 dash current flows into it, and another case when you have a voltage source at V 2, like same voltage source you apply at V 2 and we short the input terminal, or you can call it the then the current flows I 1 dash. So, but the source voltage are the same, and we say this current are flowing on other side I 2 dash and I 1 dash. So, a network is said to be reciprocal if we can say I 1 dash equal to I 2 dash, and that define I 1 I 2 dash are defined here, or we can say in terms of this we can define when the Z12 equal to Z21, because both voltage source magnitude are same. So, you can say by defining this you will get the Z12 equal to Z21, and this condition we call it that reciprocity condition for this 2 port network, and we call it that network is reciprocal. Then another condition is there for symmetry. So, a 2 port network is said to be symmetrical if its port can be interchanged without changing the port voltage and current, and then we call it like V 1 upon I 1 when I 2 equal to 0 is equal to V 2 upon I 2 and I 1 0, or we can say if these two are equal, we can say Z11 equal to Z22. Then you can call it network is symmetrical, either you excite from first port of the network or second port of the network, it looks like a same impedance typically in other side keeping open circuited. So, this we call it the symmetry of the 2 port network. So, now coming to typically Z parameter analysis of 2 port network. So, we just a typical example we consider, let us say we take this network and at the output we consider the load impedance, we call it Z2 ZL at the output. So, we can say here now you will see this V 2 will be minus I 2 ZL, because the voltage will be there, current will be flowing through I 2 across through ZL also going to 2 port network. So, we can keep value of course V 2 in this, and we can simplify the typically this network. And so, now we can say same matrix form V 1 V 2 equal to Z I 1 in terms of I 1 I 2 with the impedance parameters, we can say Z11, Z12 and Z21 and Z22, and we can put the value of V 2 equal to minus ZL I 2 for the condition of this network and rearranging the equations. So, when we rearrange, when we put the value of V 2 and this we take on other side. So, here it is a minus, it will go other side plus. So, it will become V 1 0 equal to Z11, Z12, Z21 and Z22 plus ZL as a function of I 1 and I 2. So, that equation gets simplified when we are connecting like a kind of passive network or the ZL impedance at the output terminal or one terminal. And from Cramer rule we can solve these two typically this equation for I 1. So, when you solve this equation in I 1 in terms of V 1 and the impedance parameter including the load impedance, you put the value of this matrix form and you get this of course solution for I 1 equal to Z22 plus ZL V 1 divided by Z11 Z22 plus ZL minus Z1 Z2. So, you get the current which is drawn from the source on supply side or input side, and we can call it the input impedance is Z in equal to V 1 upon I 1, and that we can say here it is typically coming from when V 1 V 2. So, this will go on other side, this will come down. So, its expression will be this modified to it will be Z11 minus Z12 Z21 divided by Z22 plus ZL. So, that will be the your input impedance for this network when you are connecting the load across the output ZL here which is defined here. And we can say now from the second equation of that network we can put the value V 2 equal to again here, and this is the second equation of this network where we have put the V 2 equal to minus I 2 ZL another equation was I2 Z2 itself. From this we took on this side. So, just solving this from second equation, the value of I2 in terms I1, that is minus Z21 upon Z22 plus ZL into I1. And we can say from this we can have a V1 equal to Z11 I1 plus Z12 I2, and we can just keep the value here typically of I2 from this in terms of I1. So, it becomes network becomes your Z1 minus Z12 Z21 divided by Z22 plus ZL into I1, and these typically the equation which we can call it the gain Vs upon V2, V2 upon Vs, we can define the gain, and that will be V1 upon Vs into V2 upon V1. Like we can divide into two part of this gain, and then we can put the value typically the two gains if V1 in terms of the Z in divided by Z in plus Zs, and multiplied this ZL upon Z22 plus ZL into Z21 upon ZL, and this comes finally ZL upon Z22 plus ZL into Z21 upon Z in into Zs, and you can have a two circuit here. You can clearly see here Vs is applied, and we say Z in is here, the impedance seen at the V1, where this source resistance is as a part of you can call it the source, and you have this parameters representing it the first equation of I1 Z11 and the voltage source coming from the dependent voltage source coming from I2 side, and here in secondary also you have a dependent voltage source coming from primary side Z2211 and Z22. So, this represents the terminated two port Z parameters model typically for the that two port in terms of the parameters as well as the load impedance and applied voltage from input side like. So, now coming to this is the that was the example of Z parameter. So, sometimes we define the Y parameter or admittance parameters of this two port network. But there may be many parameters for this network, but we will look into which get simplified. We discussed earlier also that you can solve the equation in terms of either in terms of impedances or in terms of your admittances, depends on series and parallel circuits. So, that is the reason we have to define even the Y parameter also of this network like. So, the admittance Y parameters for again two port network. So, we have again V1 I1 on the input side, and output side we have a V2 I2, and this network equation for in terms of admittance parameters we can say I1 I2 will be equal to in terms of V1 equal to V1 V2, Y11 Y12 and Y21 and Y22. This is we call it admittance matrix. So, current can be defined as a function of admittance and voltage. So, that is exactly the matrix we are having, and this can be also written in scalar form I1 equal to Y11 V1 plus Y12 V2 and I2 equal to Y21 V1 plus Y22 V2. And we can go of course, in this case also in the same manner to define the parameters your admittance parameter by keeping a current source on the input side and keeping the secondary typically here the sorted like So, we can define the parameters Y11 will be equal to I1 divided by V1, as voltage V1 is applied here, and Y22 will be equal to I2, your current I2 is also flowing here divided by V1, the voltage applied here, how much is the current flowing into this short circuited path. So, that is your Y21. Similarly, we can define here now applying the current source on the terminal 2 and keeping sorted of terminal 1. So, we can define Y12 is I1 upon V2 and Y2 equal to I2 upon V2. So, these are the of course, the parameters we can say determine the Y parameter finding Y11 and Y21 and another is finding out Y12 and Y22. So, again we can define all these four parameters in terms of now Y1 equal to I1 upon V1 when V2 is 0 means second port is short circuited. So, I1 is the admittance looking into port 1 when port 2 is sorted or short circuited, and Y12 equal to I1 upon V2 when V1 equal to 0. So, Y12 is the transfer admittance, it is the ratio of current in at port 1 and the voltage at port 2 when port 1 is sorted, and Y21 I2 upon V1 when V2 equal to sorted. So, Y21 is the transfer admittance transfer admittance, and it is the ratio of the current at port 2 to the voltage port 1 when the port 2 is sorted, and then Y22 equal to I2 upon V2 and V1 is equal to 0. So, Y22 is the admittance seen looking into port 2 when port 1 sorted. So, these are the four parameters admittance parameters of these two port networks like. So, now condition here also we have a reciprocity condition as well as symmetry condition what we discussed already earlier in Z parameters. So, for reciprocal network we can say Y12 equal to Y21 or you and Thus, for symmetric network you can say I 1 upon V 1 at when V 2 equal to 0 equal to I 2 upon V 2, and when V 1 equal to 0, or we say Y 1 1 equal to Y 2 2. So, these are the two conditions for, this is the condition for reciprocal network, this is the condition for symmetric network like also. Now, we can typically again analyze Y parameters for the terminated 2 port. So, this is again the same 2 port network where we have a V 1 I 1 as a input and V 2 I 2 at output. So, at output we are connecting again the load Y L as we have considered the Z L earlier. So, now we are considering Y L, and we can say I 2 current flowing into this will be minus V L into V 2. I mean earlier we were keeping V 2 equal to minus I 2 Z L, now we are keeping I 2 equal to minus Y L V 2, and putting this value, this is our original equation I 1 I 2 in terms of V 1 V 2 with the admittance matrix of Y 1 1, Y 1 2, Y 2 1 and Y 2 2. And now, in place of putting I 2 from here we can put here and take the quantity on other side. So, it comes I 1 0 equal to V 1 V 2. In terms of V 1 V 2 it is Y 1 1, Y 1 2 and Y 2 2, and we of course, adding here the value of typically of Y 2, that is Y 2 2 plus Y L. So, this is a relation comes under P specific condition when a passive net admittance is connected at the output like, and from this we can certainly solve the now the equation for your V 1 from same Cramer rule by the matrix relation, and that comes equal to Y 2 2 plus Y L into I 1 divided by Y 1 1 in bracket Y 2 2 plus Y L minus Y 1 2 and Y 2 1, and then this is from first equation. Then from second equation that we can define input admittance Y 1 1 equal to typically, I mean where we can call it like I 1 upon Y 1, I mean typically from here. So, that comes equal to Y 1 1 minus Y 1 2 Y 2 1 divided by 1 1 and bracket Y 2 2 plus Y L, and typically from second equation, this is the second equation of course for the port. So, we that is Y 2 1 equal to V 1 equal to minus Y 2 2 plus Y L into V 2, and from which we can have a relation between V 2 equal to minus Y 2 1 V 1 divided by Y 2 2 plus Y L, and from which we can typically get the value of V 2, and I 1 will be then finally in terms of Y 1 1 V 1 plus Y 1 2 V 2, and because there is no, you can call it V 2 here. So, it is only the admittance here Y load admittance. So, we define everything in terms of Y 1 only, that comes equal to Y 1 1 minus Y 1 2 Y 2 1 divided by Y 2 2 plus Y L into V 1, that represents virtually on this side here as we see here Y 1 and then this is the dependent voltage source typically coming on the second side. This is the input current source, and gain will be your V 2 upon V 1, and that is your minus V 2 Y 2 1 divided by Y 2 2 plus Y L, here Y L is connected here. So, that is how we define the voltage gain and how we represent the on the input port the equivalent circuit and output equivalent circuit, of course, in terms of parallel branch, because admittance is always preferred to consider as the equivalent to parallel branch. Impedance we already considered as a series branch earlier what we discussed in the Z parameters like. So, now some little quiz questions to quick have, that here the 2 port network is shown here. So, we can say what will be the Z 1 2, that transfer impedance. So, from this of course, transfer impedance we already defined what is Z 1 2. Z 1 2 we define like when your second is open, what will the impedance V 2 your V 1 upon I 2, that will be virtually the here only Z 1, that voltage will be reflected when second is open. So, it will be directly your Z 1 1, and similarly you can have a for the 2 port network, here the value you can find out Z 2 1 in the similar manner. So, that comes by calculating the impedance from here, you will just this will come in, you have to convert kind of this into the delta connection, then it comes parallel with the 3 ohm, and similarly during the parameter of Z parameters, what is the Y 1 1 here from Z. So, you have to consider and convert into that comes, and similarly the Z parameters shown in the circuit from this. So, it comes transfer impedance is only minus 4 ohm, and similarly the parameters Y 2 2 you can find out in terms of this. So, it comes typically coming equivalent to of this here. So, these are some of course quick question you can have a quick. Now, coming to some of the solved problem, I mean compute the Z parameters of the network shown here. So, we have here 20 ohm T network with the 20, 30 and 40 ohms. Now, from this of course, we put it the input parameters Z 1 1 when the second is open and current flows into it. So, you will have a V 1 upon I 1. So, V 1 upon I 1 will be these two impedance divided by I into I 1, I mean that is the voltage is taken V 1 divided by your I 1. So, it comes like a 60 ohm, and Z 2 1 will be V 2 upon I 1. So, the voltage which will be across the 40 ohm will be reflected at the output, because there is no current in this. So, it will be 40 into I 1 divided by I 1. So, that is a 40 ohm. Similarly, we can go here now for finding out the parameter from output side. So, we apply the voltage here and keep the primary open. So, we define Z 2 to V 2 upon I 2 here. So, this will be again 2 resistance divided by the current. So, that will be 30 plus 40 will be the V 2 observed across there divided by I 2. So, it will be 70 ohm, and Z 1 2 of course, the voltage which get reflected here, it will be your V 1 I 1. So, that will be again the current flowing into the 40 ohm, that voltage, because there is no current. So, it will be reflected here. So, it will be 40 into I 2 divided by I 2, and that will be 40 ohm. So, we can say now Z parameters we got it equal to Z 1 1, Z 1 2 and Z 2 1, Z 2 2, putting the value here, it comes 60, 40, 40 and 70. I mean, so, we can say that this network is your reciprocal network, because your Z 1 2 equal to Z 2 1. Now, coming to numerical 2, compute the Z parameter of the circuit shown here. We have a R 1, R 2 and R 3, I mean typically in form of the delta connection, and from which we can find out like a parameter V 1, I mean by of course, V 1 will be equal to I 1 minus I 3 into R 1, that you can keep equal to I 1 R 1 I 1 minus R 1 I 3, and V 2 will be your from this side will be I 2 plus I 3 into R 3, and this will be R 2 R 3 I 2 plus R 3 I 3, the voltage at typically V 2, and the third, the loop equation will be here equal to 0, that will be R 1 I 1, here I 1 current is typically plus R 3 I 2 plus R 1 plus R 2 plus R 3, that is the I 3 is flowing in the all 3. So, that represent this, and this is 4 of course, with the minus here, because just polarity is opposite, I 1 I 2 are opposite here, and plus R 3. So, from solving this network we will get value of I 3, I mean from the this equation. So, we will get R 1 divided by R 1 plus R 2 plus R 3, dividing this equation from this. So, we will get R 1 into I 1 divided by R 1 plus R 2 and minus R 3 into I 2 divided by R 1 plus R 2 plus R 3. So, that is the I 3 value, which we can keep I 3 into that network. So, we get V 1 in terms of I 1 and I 2, and that relation comes between, and V 2 we get in terms of again I 1 I 2. So, certainly you are getting now the 4 parameters, you can call it, this is your Z 1 1, Z 1 2, and this is Z 2 1 and Z 2 2, and you can say now in matrix form Z 1 1, Z 1 2 and Z 2 1, putting the value of all these circuit parameters here. So, this comes as a complete parameters, Z parameter of this circuit like also. Now, given the coming with the numerical 3, given the circuit, determine the Z parameter of this. So, we have a 3 resistance in delta connected mode with the 8 ohm on this side, similar to the previous, except we add this resistance also. So, now we can see in this network, when second is open, we have to solve what is Z 1 1. So, Z 1 will be 8 plus this your 20, and typically in parallel with 30, that comes 20 ohm, that is Z 1, and Z 2 2 will be your typically your this 30, this 30 in parallel of 20, that Z 2 2, that is 12 ohm, and that is what we are defining Z 1 2 V 1 upon I 2 equal to 1, and that comes your V 1 in terms of typically here 20 into I 3 into I 2 divided by 20 plus 30. So, that is 8 I 2, and from which we can get Z 1 2, and that comes typically your Z 1 2 equal to 8 ohm, and similarly the. So, all typically we got the 4 parameters. So, hence we can write here the same V 1 V 2 in terms of this current, and Z 1 2 Z 2 1, and V 1 V 2, that 28 into 8 into 10 12. So, here also we can say this network again is a reciprocal, because Z 2 1 equal to Z 1 2. Coming to numerical 4, here we have been given the network, find the impedance parameter. So, other than resistances, we have here a kind of a dependent voltage source. So, what is the voltage here? That is the 2x voltage source is applied here. So, now we have to of course solve these Z parameters by taking the equation. So, we have to keep like a from primary side, we have to keep secondary open. So, from this what we define V 1 upon I 1 when I 2 equal to 0. So, we can say here I 1 equal to V x upon 1, that is the typically the current flowing into here, plus V x plus 2 V x divided by 6, taking this loop network. So, it becomes 6 V x plus 2 V x by 2. So, I 1 equal to 3 V x by 2 or V x equal to V 1 minus I 1, and substituting this value you will get I 1 3 V 1 minus I 1 by 2 or V 1 upon I 1 equal to Z 1, that is 5 by 3 ohm. And typically similarly you can find out the other 3 parameters also keeping the condition. So, you will get all 4 parameters here. Now, coming to numerical problem 5, determine the admittance parameter from the circuit shown there. So, we have here Y 1, Y 2 and typically a current source with the 0.5 V 1 dependent current source which depends on input voltage. So, here we can just keep I 1 equal to Y 1 V 1, that is the current going here, and Y 2 equal flowing Y 1 minus Y 2, because the voltage across this is V 1 minus V 2, and that solving it will be Y 1 plus Y 2 into V 2 minus Y 2 V 2, and I 2 will be of course here drawn from here when I 1 made 0, 0.5 that is the current plus Y 2 V 2 Y 3, that is the current flowing into it, and the another set of current is flowing here, that is typically Y 2 minus V 1 V 2 across this, and then the typically the volt. So, from this solving this you will get Y 5 minus V 1 plus Y 2 plus Y 3 equal to into V 2. So, this we represent in terms of V 1 V 2, here also V 1 V 2 I 2 I, and putting I 1 I 2 in terms of V 1 V 2. So, you have a parameters here, first parameter, that is Y 1 1 will be Y 1 plus Y 2 and Y 2 2 will be your minus Y 2, and Y 2 1 will be 0.5 Y 2 and Y 2 2 will be Y 2 plus Y 3, and this becomes the parameters here for this network, your admittance parameters of this network. So, here again given the circuit, find the Y parameter here with the 3 resistances at 20 ohm, 5 ohm and 15 ohm with this network typically. So, we can say second is sorted. So, we say V 1 equal to typically V 2 equal to 0. So, we say V 1 equal to 20 I A, that is the current flowing into here, and I A equal to 5 upon 25 I 1, that is the division of the current flowing into here. So, putting this Y 1 will be I 1 by 1, that is 1 by 4 Siemens, and then V 1 equal to minus phi 1. So, Y 2 will be I 2 upon V 1, that is minus 1.1 by 5 Siemens, and similarly we can find out from now primary sorted and applying the V 2 here. So, V 1 is 0. So, V 2 equal to 15 I x, and you can find out I x 5 by 25 typically I 2, and putting this we get Y 2 equal to I 2 V 2 equal to 4 by 15 Siemens, and then we got typically all 4 parameters here. So, Y parameters in Siemens 1 by 4 minus 1 by 5 minus 1 by 5 and 4 by 5. This is also you can see the reciprocal network, because your Y 1 to 1 equal to Y 1 2, and this is typically the another Y 1 2 and the another final parameter. So, coming to numerical 7, find the Y parameters for the circuit where you have a dependent voltage source, current dependent source of the I 2 current here, and remaining are the other elements like impedance network element. So, keeping the V 2 sorted, because we are interested admittance parameter. So, from which we can get V 1 equal to your 2 plus J 4 into I 1, and Y 2 equal Y 1 1 will be I 1 Z 1. So, it will be 1 upon 2 plus J 4, that is equal to 0.1 minus J 0.2 Siemens, and Y 2 1 will be I 2 upon V 1, that is equal to 0 Siemens, and then you have a like now V 1 equal to 0, and resolve the circuit. They will get I 1 equal to in terms of this minus Z 4 typically Z 10 I 2 divided by 2 plus J 4, typically this impedance that comes. So, from here you can have a now putting the value here I 2 will be V 2 minus J 20, and that is the node application V 2 minus Z I 2 divided by 10. So, it just putting value you can just keep to I 2 equal to V 2, just taking out. So, 1 upon 10 plus minus 1 upon 20. So, from this we can have Y 2 equal to I 2 upon V 2, that comes 0.05 in plus J 0.05, and then Y 1 2 equal to I 1 upon V 2 equal to minus 0.1 plus J 0.075 Siemens, and in matrix form Y becomes like 0.1 plus J 0.2 and minus 0.1 plus J 0.075 0.05 plus J 0.025. It is not neither symmetrical or not reciprocal network like. Now, there are some unsolved problems which you can solve in the same manner. Just an example, typically your for the purpose of your, and these are the of course, the references from which we have develop this lecture like, and thank you very much like.